Have you ever wondered why certain traits or health conditions are more common in some groups of people than others, or how scientists piece together the story of human migration across continents? It is like trying to solve a vast puzzle where every piece, no matter how small, holds a clue about the bigger picture. Understanding population structure is critical because it reveals how genetic diversity is organized within and between groups, providing fundamental insights into evolution, health, and human history. It acts as a roadmap to the genetic landscape of any species, including our own, explaining patterns we observe in biology and anthropology. The core reason this is so important lies in how different forces shape the genetic makeup of populations over time. Population structure helps us see the invisible boundaries and connections between groups, influenced by things like physical distance, cultural practices, or even historical events. It is not just about counting genes, but understanding their distribution. Are certain gene variants common in one area but rare in another? This tells us about past isolation or gene flow. Genetic drift, natural selection, mutation, and migration are the evolutionary forces constantly at work, molding this structure. For example, a small, isolated group might accidentally lose genetic diversity due to random genetic drift, while a large, well-connected population maintains it through constant gene exchange and migration. This insight allows us to infer historical demographic events, like population bottlenecks, expansions, or admixture events, all of which are crucial for understanding human origins and movements across the globe. For researchers, understanding population structure means carefully selecting study populations to avoid spurious associations in disease studies, a phenomenon known as population stratification. For conservationists, it means identifying genetically distinct populations that requiring separate management plans to ensure their survival and maintain biodiversity. And for anyone studying human history, it means using genetic markers to reconstruct ancestral paths and clarify relationships between ancient and modern human groups, painting a vivid picture of our shared past. To add an extra layer of insight, consider the concept of FST, or fixation index. This is a powerful statistical measure of genetic differentiation between populations. A high FST indicates significant genetic differences, suggesting long-term isolation, while a low FST implies more genetic similarity due to recent shared ancestry or ongoing gene flow. Another key term is gene flow itself, which refers to the movement of genes between populations, acting as a powerful homogenizing force that can reduce genetic differentiation. We can also differentiate between a panmictic population, where all individuals have an equal chance of mating, versus a structured population, where mating is non-random, leading to genetically distinct groups. By grasping these principles of population structure, we gain powerful tools to unravel the mysteries of biological adaptation, trace our ancestral journeys, and even pave the way for more targeted and effective medical interventions. It ultimately helps us appreciate the deep interconnectedness and subtle distinctions across life on Earth, providing a foundation for understanding both our individual traits and our collective human story.